Hello learners, and welcome to your video tutorial over universal gravitation. Now, when we're doing problems like this, we're generally going to veer away from weight is equal to mg. Now, this is all well and good when you're talking about an object that is near the surface of whatever is creating your g. But whenever you get further out from a particular planet, well, that distance of how far you are out will change your weight. And so universal gravitation is g m1 m2 all over r squared. Now that r is the distance between your two objects' centers. So let's say I've got a red-bodied star and then a very tiny planet over here. Well, r is going to be from this point to the center of the planet. Now, it's not surface to surface, it's not back surface to back surface, it's center to center. That is your r. Now, the weight or the force due to gravity between each planet is directed from that center to each other. So if this body over here, we call it M1, and we call this body over here M2. Well, each one exerts an equal but opposite direction force on each other. So the force of gravity on this planet is going to be the same as the force of gravity on this planet, but they're just in opposite directions of each other, which means the moon orbiting around the Earth, well, the Earth is exerting a force on the moon, and the moon is exerting an equal force on the Earth. So it's proportional to 1 over r squared. So the further out these two objects get, the less and less force there is between each other. The closer the objects get, the more force of gravity there is between each object. It's kind of like a magnet and a refrigerator door. If you have the magnet far out from the refrigerator door, there won't be a whole lot of force, but the closer you bring that magnet, the more and more force there will be. Now, a lot of times, a very popular multiple choice type question is something like this. You have a planet with a mass capital M and a radius r. Okay, well, you go to this new planet, which has maybe 3 times as much mass as your old planet. We'll call this one planet 1, and we'll call this one planet X. Okay, so we've got a new planet 3 times as massive, and its radius is twice as much, so 2r. Now, on this planet, planet 1, you have a weight of, let's just say, 400 newtons. Okay, well, they want to know maybe your weight on planet X. What would your weight be? Well, on planet 1, your weight is just equal to big G, M, the mass of the planet, and then your mass. So let's say you're right here. Let's say you have a mass M2. Well, M1, M2, the two masses that you're talking about, divided by r squared. That's your weight on planet 1. Your weight on planet X, I'll call it FGX. Well, it's still big G, but now the two masses, your mass hasn't changed. So it's still M2, but now it's times 3m over 2r squared. It's still over r squared, but your r is now 2r. Well, let's clean this up a little bit. So I have FGX being equal to, well, I'm going to pull this 3 kind of out here a little bit. So I've got 3G, big M, M2, all over, well, 2 squared is 4r squared. Well, if you look, I've got Gm m2 over r squared, Gm m2 over r squared. The only thing that's different is I've got this 3/4. So what I can do, FGX is 3/4 this, which is that, which is that, which is that. So on planet X, you weigh 3/4 of what you weigh on FG1. Even though the planet is 3 times as big, it's got twice the radius. So you weigh 3/4 as much you weigh on FG1. Well, your weight on FG1 was 400 newtons. Well, 4 goes into that 100, which means you weigh 300 newtons on planet X. Very popular multiple choice question.